James Webb just saw 3I/Atlas for the first time, and it shouldn't be possible. Right now, while you're reading these words, something is happening that almost nobody on Earth knows about. A small, dark object is racing away from our sun at tens of kilometers per second. It is not from here. It carries chemistry that does not match anything formed in our solar system. It was built before our sun existed, before Earth formed, before even the first simple stars had finished their lives in many parts of the galaxy. It measures less than 1 kilometer across, roughly the width of a small neighborhood in a city. Yet this single object is forcing astronomers to rethink how and when material in the universe can form the building blocks we see today. The researchers are not using words like interesting or unexpected. They are using words like astonishing, baffling, and we were wrong. This is the story of 3I/Atlas. And here is the part the headlines are not telling you. It is not just what James Webb found. It is what it found that directly affects how we understand the raw materials that eventually became you and me right here on Earth. It is what is happening to it right now in 2026 that nobody is talking about. And it is what is going to happen as it leaves our solar system forever, a journey already locked into the calendar. Stay with me, because by the time this is over, you will never think about comets or the age of the stuff that made our planet the same way. Let's go back to where this story actually begins. In July 2025, astronomers using the Atlas telescope system in Chile spotted a faint moving point of light. It was a routine survey for near-Earth objects, but within days, calculations showed the orbit was hyperbolic, open, not closed. This visitor was not bound to the sun. It came from interstellar space. It became the third confirmed interstellar object to pass through our solar system. 3I Atlas. The 3I matters. First interstellar was 1 in 2017. Second was 2I Borisov in 2019. This is the third, and it is already the most chemically revealing. Fast forward to August 2025. The James Webb Space Telescope turned its near-infrared spectrograph toward this visitor. Then, in December 2025, after 3I/Atlas had passed closest to the sun, Webb looked again with its mid-infrared instrument. These were not quick snapshots. They were careful chemical fingerprints, taken as the comet headed back into the cold. Researchers estimate 3I/Atlas formed 10 to 12 billion years ago. 10 to 12 billion years. That number is going to come back. 10 to 12 billion years. Nearly 3 times the age of our 4.6 billion-year-old solar system. 10 to 12 billion years. This object is not just old. Its chemistry suggests it spent its formative years in conditions very different from the warm disk that made our sun and planets. How do we read the age and history of something we cannot touch? Step by step, light from the sun hits the comet. Some of that light is absorbed by molecules on and inside it. The rest scatters or is re-emitted. James Webb collects that light and spreads it into a spectrum, a chemical barcode. Certain wavelengths are missing or strong. Those missing lines tell us exactly which molecules are present. Webb detected methane for the first time on an interstellar object. It saw unusually high carbon dioxide. It measured ratios of deuterium, heavy hydrogen, that do not match solar system comets. Those ratios do not simply appear. They form under very specific temperatures and times, in cold, dense clouds. The chain is clear. 10 to 12 billion years ago, during what astronomers call cosmic noon, a peak in star formation, a dense cloud collapsed. Grains of ice and dust stuck together. Volatiles like methane and carbon dioxide froze into the mix. The object grew, but never got too close to a hot young star that would cook away its most fragile ices. Those ancient ices survived. They traveled for billions of years through the galaxy. Then, in 2025, they entered our solar system and passed close enough for Webb to read them. 10 to 12 billion years. That refrain matters because it sets the scale. 10 to 12 billion years means this comet is a time capsule from when the Milky Way was still young and busy forming stars. None of this was easy. 3I/Atlas is small, less than 1 kilometer across. It is faint. It is moving fast. By the time Webb observed it post-perihelion in December 2025, it was already heading out again. Signal travel time from the telescope to Earth is not the issue here, but the precision required is. Webb orbits the Sun at the second Lagrange point, about 1.5 million kilometers from Earth. Its instruments must lock onto a tiny moving target against the black of space. The power available for such observations is limited. The telescope itself uses careful planning to point accurately for the needed exposure times. No repair is possible. Once data is collected, it must be right. Researchers had one set of good opportunities. They used them. The result: direct detection of methane and detailed isotopic ratios that earlier telescopes could not achieve. This should not have been possible with such a small, fast-moving ancient visitor. But it happened. 10 to 12 billion years. Less than 1 kilometer across. Third interstellar object. Those numbers keep returning because they define the improbability. The first big finding hit immediately. James Webb detected methane gas coming from 3I/Atlas. Methane is highly volatile. It turns from solid ice to gas very easily when warmed. In our solar system comets, much of the original methane is usually gone or transformed by the time they reach us. Not here. Webb's mid-infrared instrument caught the clear chemical fingerprint in 2026 data as the comet moved away from the Sun. This is not a trace amount. It is enough to show the object preserved primitive ices that should have been lost over billions of years of travel. That contradicted the simple model. Many astronomers expected interstellar objects to be cooked or stripped by radiation and time. 3I/Atlas was not. Its surface and near-surface layers still hold material formed when the universe was far younger. Picture it: a dark object the size of a small neighborhood, carrying chemistry from 10 to 12 billion years ago, releasing methane you could, in principle, smell if you were close enough, though you never will be. That scale comparison makes the preservation striking. 10 to 12 billion years old, less than 1 kilometer across. What remains unexplained? Exactly how the methane stayed trapped through galactic cosmic rays and heating events during its long journey. Researchers still cannot fully explain the retention mechanism. Next came the carbon dioxide. Webb showed 3I/Atlas is unusually rich in CO2 compared to solar system comets. Carbon dioxide ice forms in very cold regions, far from a star. The ratios suggest the comet formed in a dense, cold cloud far out in its original system. Step by step, heavy elements from earlier star generations seeded the cloud. Temperatures stayed low enough for CO2 and other volatiles to freeze onto dust. The object coalesced. Then it was ejected, perhaps by a passing star or gravitational interactions, into interstellar space. This directly challenges models that assumed most interstellar comets would look chemically similar to our own. 3I/Atlas does not. Its composition points to a parent star system that was itself ancient, likely in the Milky Way's thick disk. 10 to 12 billion years. Third interstellar object. The numbers keep landing. An object less than 1 kilometer across, yet chemically distinct enough to rewrite expectations for what drifts between stars. Researchers are not hiding the gap. The exact ejection mechanism and the full history of its parent system remain close to impossible to reconstruct with current data. Deuterium ratios delivered another surprise. Deuterium is heavy hydrogen. In cold environments, certain molecules end up with higher deuterium fractions. Webb's measurements on 3I/Atlas show levels that fit formation 10 to 12 billion years ago during cosmic noon, when star formation was intense and clouds were dense and cold. Compare that to our solar system comets. Different deuterium fingerprints. The difference is not subtle. It is like comparing ice from two entirely separate freezers with different temperature histories. This finding affects you right here on Earth. The raw materials that made Earth's oceans and atmosphere likely came from similar cold cloud chemistry 4.5 billion years ago. Seeing a pristine sample from much earlier helps calibrate how common, or rare, those conditions were. The data came from December 2025 observations, post-perihelion, when the comet was cooling again and releasing its most volatile contents cleanly. James Webb caught it at the right moment. 10 to 12 billion years old. Less than 1 kilometer across. The refrain underscores the improbability. A visitor from deep time, studied with a telescope that launched in 2021, revealed details no one expected. What remains unexplained? Why this particular object survived intact, while others may have been destroyed or altered beyond recognition. One more key piece. Webb and supporting observations showed 3I/Atlas has a mix of carbon monoxide, carbonyl sulfide, and even traces similar to some solar system comets in cyanide and nickel, but the overall package is unique. The mechanism, As the comet approached the Sun in 2025, ices sublimated in sequence according to volatility. Webb's instruments mapped the resulting coma, the cloud of gas and dust around the nucleus. The spectrum told the story of layered ices preserved for 10 to 12 billion years. This should not have been possible. Interstellar space is harsh, yet here it is, the third confirmed interstellar visitor, carrying a chemical library from when the galaxy was still building its disk. The power of Webb's instruments, operating far from Earth with limited but precise energy, let us read signals that ground telescopes could not isolate. Those signals travel across vast distances before reaching us. The numbers land again, 10 to 12 billion years, less than 1 kilometer, December 2025 data. Honest unknown. Scientists cannot yet say with certainty whether objects like this delivered crucial organics to young planets across the galaxy, including possibly ours. The data is suggestive, not conclusive. Let us slow down on one of the most important contradictions, the age estimate itself. Astronomers combined Webb's chemical data with dynamical modeling and comparisons to stellar populations in the Milky Way. The result, 3I/Atlas, most likely formed between 10 and 12 billion years ago, 10 to 12 billion years. That places its birth during cosmic noon, a period when the universe was forming stars at a furious rate, galaxies were colliding more often, and dense molecular clouds were common. Our own solar system formed only 4.6 billion years ago. This means 3I/Atlas is nearly 3 times older. It has been wandering the galaxy for more than twice the entire history of our planetary system. How do they reach that number? Isotopic ratios, especially deuterium to hydrogen and carbon-13 to carbon-12, act like cosmic clocks. In cold clouds, specific reactions favor heavy isotopes. The longer the material sits in those conditions without being heated, the more extreme the ratios become. Webb measured those ratios directly in the gas released by the comet. The match points to an ancient origin, 10 to 12 billion years. Less than 1 kilometer across. Third interstellar object. These signature numbers are not decoration. They quantify the shock. An object the size of a modest city block has traveled through the galaxy longer than Earth has existed, and it still carries readable chemistry. This finding contradicts earlier assumptions that interstellar comets would be heavily processed or that material from such early times would be too dispersed to form coherent bodies. Researchers openly say the preservation challenges models of galactic chemical evolution. Some material from the early Milky Way survived in ways we did not predict. What remains unexplained? The precise path 3I/Atlas took over those billions of years. Did it pass through dense regions that would have eroded it? How many close stellar encounters did it survive? The data cannot yet trace the full route. Think about the scale again. If you drove a car at highway speed non-stop, it would take you roughly 100 years to reach the nearest star. This comet has been traveling at interstellar speeds for 10 to 12 billion years. The distance covered is beyond everyday imagination. Trillions of times the Earth-Sun distance. Yet Webb caught it during its brief passage through our neighborhood. Another layer, the nucleus size and activity. Hubble and other telescopes constrained the nucleus to less than 1 kilometer, possibly much smaller. Despite that tiny size, 3I/Atlas showed a detectable coma when closest to the Sun in late 2025. It released gas and dust in measurable quantities. Small bodies should lose their volatiles faster. They have less mass to shield ices inside. Yet 3I/Atlas still had enough methane, carbon dioxide, and other species to produce clear signals for Webb in December 2025, after perihelion. This is the mechanism in plain steps. Solar heat reaches the surface. Volatile ices sublimate directly to gas. Gas drags dust with it, forming the coma. Light from the Sun scatters off that coma and is re-emitted at specific wavelengths. Webb collects those wavelengths and decodes the molecules. Each step is simple physics. The surprise is that the steps still worked after 10 to 12 billion years of exposure. The object did not go dormant or lose everything. It retained enough primitive ice to become active again near our Sun. Compare it to a freezer left unplugged in a garage for decades. You would expect everything to have thawed and evaporated long ago. Yet this cosmic freezer still had measurable contents. That is the power of the vacuum of space and the protection of buried layers. but only up to a point. The fact it worked at all is what researchers call baffling. 10 to 12 billion years old. Third interstellar object observed. Less than 1 kilometer across. December 2025. WIST data. The refrain returns, because each repeat reminds us how unlikely a clean look at such ancient material really is. Honest unknown. We do not know if 3I/Atlas is typical or an outlier. With only 3 interstellar objects confirmed, statistics are almost non-existent. It could be that most such visitors are destroyed or too faint to study. This one happened to pass close enough, at the right time, for our telescopes to catch it. So where does this go next? 3I/Atlas is already leaving our solar system. Its hyperbolic orbit means it will never return. It is accelerating away, back into interstellar space, carrying its remaining ices with it. At some point in the coming years, it will become too faint even for Webb or the largest ground telescopes. The last useful data will trickle in, then silence. But even when that happens, the scientific work does not stop. Teams are still analyzing the full dataset from the 2025 and 2026 observations. Papers will continue to appear. Models will be updated. The chemical fingerprints of 3I/Atlas will be compared to future interstellar visitors, if we are lucky enough to find them. In the 2030s, new facilities like the Extremely Large Telescope and planned space missions may be ready for the next one. ESA's Comet Interceptor, launching around 2029, is designed to wait at a Lagrange point for a suitable target, though catching another interstellar object would be extraordinary good fortune. The real long-term impact is on our broader understanding. 10 to 12 billion years. That age tells us that complex chemistry, the kind that eventually led to planets and life, was possible very early in galactic history. It suggests that the ingredients were widespread. It raises the possibility that places like Earth are not as unique in their starting materials as we once thought. Yet the object itself will continue its journey for billions more years, perhaps eventually passing through another star system. There is nothing to stop it. No friction in interstellar space, no decay clock that runs out anytime soon. It will keep traveling, a silent messenger from cosmic noon, until gravity or a collision changes its path. This single small visitor, less than 1 kilometer across, has already done something remarkable. It gave us a direct sample of material from when the Milky Way was still forming its structure. December 2025, observations by James Webb turned a faint point of light into a window on deep time. Researchers still cannot fully explain how so much primitive material survived. The preservation remains close to impossible under some older models. That tension is where the science lives. Expanded reflection for depth. Consider what this means for the trillions of other small bodies drifting between stars in our galaxy alone. If even a fraction carries similar ancient chemistry, then the universe has been seeding itself with potential building blocks for a very long time. 10 to 12 billion years is not just a number. It is a reminder that our solar system formed relatively late in a long story of galactic recycling. The atoms in your body, the water on Earth, some of their precursors may have had cousins in objects exactly like 3I/Atlas. The third interstellar object showed us that. And in 2026, as it continues outward, we are still only beginning to understand the message. So what does all of this actually add up to? One small comet, 10 to 12 billion years old, less than 1 kilometer across. The third interstellar object we have ever confirmed, observed in detail during December 2025 as it left our solar system. James Webb gave us a clean look at chemistry from cosmic noon, a time when the galaxy was far more active than today. That chemistry does not match our local comets. It survived a journey longer than the age of our sun, and it forces us to accept that the raw materials for planets and possibly life were available across the Milky Way much earlier than we assumed. This is not hype. It is a quiet expansion of the possible. An ancient visitor passed through, left its spectral fingerprint, and is now heading back into the dark. When it eventually goes quiet for our telescopes, the answers it carried go quiet with it, at least until the next one arrives. 10 to 12 billion years, less than 1 kilometer across. Third interstellar object. December 2025. JOICE data. These numbers form the closing rhythm. They mark how unlikely the observation was, and how valuable. It is genuinely worth wondering what else might be hiding in the trillions of small bodies drifting between the stars. Objects just like this one, carrying their own stories from the early galaxy. If you found this useful, hit subscribe and turn on notifications. This channel breaks down real space discoveries, grounded in published research rather than exaggerated headlines. No guessing, no dramatizing, just the data, the context, and what it actually means. Stay curious. The universe is still writing the rest of the story.